Let's begin our journey into the applications of differentiation by working with related rates problems, kind of problems and situations that involve more than one rate of change. So related rates problems allow us to handle situations in life where there's more than one thing that's changing. You can see some examples here. So the first thing we're going to do in a related rate problem is make a sketch, make a picture, label it, and put all the constants and values down that we know and that we're trying to find out. And when we're doing this, it's important to note that things that are increasing we're generally going to call positive, and things that were decreasing we're going to call negative. Then you're going to write an equation that relates them together, relating the quantities with the unknown rates of change with the other rates of change that we do know. Then you're going to differentiate, and almost always that's going to be implicit differentiation, and solve for the unknown rate. And finally, and only finally, do you substitute numbers in for the given values and simplify. Common mistake on related rates problems is to substitute numbers in earlier than the very ending. You want to wait until the end because those numbers are usually only good at a specific instance in time. So let's look at a very generic example. Suppose we have two quantities x and y that are both differentiable functions of t, time, and are related by the equation y equals x squared plus 3. We're going to find dy dt if we know that at the instant that x equals 1, dx dt is equal to 2. Now you've got to avoid the idea that you're going to just put numbers in right away. You don't want to do that. In this case, we already know that the two variables are related with this equation. And there's really no picture to draw at this point. So the derivative of y with respect to t is equal to the derivative of x squared plus 3 with respect to t. So we're going to differentiate the function with respect to t. dy dt is equal to 2x times dx dt. Now at the instant x equals 1 and dx dt will equal to 2, we can actually figure out what the rate of change is of y. And we do that by substituting in 1 for x and a 2 for dx dt. So it becomes 2 times 1 times 2, or 4. Let's look at a situation where air is being pumped into a spherical balloon at a rate of 10 cubic centimeters per minute. We want to know how fast the radius of the balloon is increasing as that air is going in. At the instant, the radius is 5 centimeters. So let's tie it all together. We'll let V be the volume, R be the radius, and we know that those two things are related by the volume formula for a sphere. It's a spherical balloon. So V is equal to 4/3 pi r cubed. And if we differentiate both sides with respect to time, dV dt is going to be 4/3 pi times 3r squared dr dt. Don't forget about the dr dt part. This is related rates. We're implicitly differentiating this with respect to time. If you simplify that, the 3's are going to cancel out and you get 4 pi r squared dr dt. But what we're interested in doing this is solving it for dr dt because it's dr dt, the rate of change of the radius that we're trying to find. So let's divide both sides by 4 pi r squared to get the dr dt by itself, and that becomes an easier way to solve this for dr dt. Now and only now we can start putting numbers in. We know that air is going into this balloon at a constant rate of 10 cubic centimeters per minute, so dV dt is 10. We're trying to find the rate of change of the radius at the instant r equals 5 centimeters, so r is going to equal to 5. And so we know dr dt is 1 over 4 pi r squared dV dt, and substituting in numbers now and only now, we're going to get dr dt is equal to 1 over 4 pi times r squared, 5 squared, which is 25, times dV dt, which is 10, and that gives you 0.0318 centimeters per minute. Let's look at an example of throwing something into a pond. If you've ever dropped or thrown a stone into a pond, you know that it causes ripples. If you drop it the right way into a calm pond, the ripples will form circles. The radius, and let's call it R, of one of the ripples is increasing at a rate of 1 foot per second. When the radius is 4 feet, the radius of your ripple, at what rate is the total area of the disturbed water changing? So let's think about what it is we know. We know the instant in time the radius is 4 feet. We know there's some relationship in a circle between area and radius, and the radius is increasing at a rate of 1 foot per second. And what we're trying to find out is what's the rate of change of the area at that instant. So let's relate radius and area in a circle, and of course you know that the area of a circle is pi r squared. So that's our primary equation that's going to relate these two things. Let's differentiate that with respect to time. The rate of change of area with respect to time is equal to the rate of change of pi r squared with respect to time. So we'll implicitly differentiate that, and we get dA dt is equal to 2 pi r, the derivative of pi r squared, dr dt. Well, this is already solved the way we want it because it's dA dt that we're trying to find, and it's r at the instant we know, and we know that dr dt. So we know that the radius of the ripple is increasing at a rate of 1 foot per second. So dr dt, rate of change of the radius with respect to time, is 1. At the instant we're looking at is when the radius is 4 feet, so r is going to equal 4 feet. We take that equation, and we're going to put in the 1 for dr dt, and we'll put in a 4 for r, and we get the rate of change of the area is with respect to time is equal to 2 pi times 4 times 1, which is equal to 8 pi, or approximately 25 square feet per minute. Let's look at another example. Suppose we have a patrol car parked 50 feet from a long warehouse, and the revolving light on top of the car turns at 30 revolutions per minute. How fast is the light beam moving along the wall when the beam makes angles of 30 degrees, 60 degrees, and 70 degrees with a line perpendicular from the light to the wall? Now, drawing a picture is essential here to get an idea of what's going on. And it's that angle theta that's changing from 30 degrees up to 60 degrees and eventually to 70 degrees. 30 revolutions per minute means that d theta dt is equal to 30 times 2 pi, or 60 pi radians per minute. And 60 pi radians per minute, another way to write that is pi radians per second. When you look at this triangle, you see it's a right triangle, and x and 50 are the opposite and adjacent sides of the triangle if theta is the angle we're interested in. So opposite and adjacent means we're going to use tangent. Therefore, the tangent of angle theta is equal to x over 50. And x is that distance along the wall that the shadow is moving. So if we take the derivative of both sides here, we're going to get secant squared theta d theta dt equals 1 over 50 times dx dt. Now, solving that for dx dt, because it's this rate of change of the shadow on the wall we're interested in, we move the 1/50th to the other side by multiplying both sides by 50. So dx dt is equal to 50 secant squared theta d theta dt. So when theta is equal to 30 degrees, dx dt is going to be 50 times the secant squared of 30 degrees times d theta dt, which is pi, which is 200 over 3 pi feet per second. At 60 degrees, it becomes 50 secant squared of 60 times pi, which is 200 pi feet per second. So you can see that rate is increasing as the angle increases. And at 70, it becomes approximately 427 pi feet per second. In fact, at 90 degrees, it becomes infinity because the secant of 90 degrees is infinite. You remember secant is 1 over the cosine. At 90 degrees, the cosine would be 0, so it would go to infinity at that point. So we've just looked at 4 examples of how to do problems involving related rates when there are more than one thing that are changing, and those things are related to each other, usually by time.